So I was mentioning to you, bytes have not always been 8 bits. Um, the what people were grappling with is they wanted a way to represent English letters, right? The history of computing is largely based on developments in English-speaking countries. Um, Now, as the ASCII table shows, you need at least 7 bits to represent letters, numbers, and punctuation. And if you think about it, it's pretty easy to see why, right? Okay, so you need upper and lowercase letters. So that's 52 characters, right? Plus digits. Okay, now we're up to 62, 0 through 9. And 62, hey, that's less than 64. So it potentially fits in 6 bits. But then you add punctuation. And there's a whole lot of punctuation characters. I mean, if you go back to that ASCII table in the exercises, right? We've got all of these punctuation characters salted in here. And so that blows you past 64 characters that you need to represent. And so that forces you to have at least 7 bits to represent letters and numbers and all that stuff. But you're like, okay, well, we're up to 7 bits. Maybe we should go to 8 bits because it's the next power of 2, right? And computers like numbers that are powers of 2. And so if you want to think of it that way, it's just like you need at least 7 bits to represent all English characters, including punctuation, and then 8 is the next power of 2 up. It kind of makes sense for why bytes are 8 bits. The reality is a little bit more complicated. There's actually a little bit more of technology history that ties into why the byte that we know and love today ended up being 8 bits. And this is stuff that mostly happened in the 1960s and 70s. In the 1960s, AT&T, which was the only phone company at the time in the US, went to a digital telephony infrastructure. And they used an 8-bit ULAW encoding for encoding telephone calls in the earliest digital telephony systems. So, well, it's like, okay, the phone company standardizing on 8 bits. We need to make equipment that the phone company uses. Maybe we should use 8-bit bytes. The other thing that happened in the 1960s is that mainframes, 16-bit mainframes became very common. IBM, DEC, all of these different mainframe companies, seem to have standardized on 16-bit processors. Also, IBM in the 1960s introduced their character encoding EBCDIC, which I mentioned earlier, extended binary coded decimal information coding. And so EBCDIC was a competitor to ASCII that IBM created. And EBCDIC, because it did binary coded decimal, actually ended up wanting 8-bit bytes. So EBCDIC was an 8-bit character set that was used in IBM mainframe equipment. Okay. So all of that kind of converged in the 1960s and made 8 bits kind of the standard for a byte and 16-bit be kind of the standard for processors. In the 1970s, we started seeing commercial off-the-shelf microprocessors being created. First 8-bit, then 16, and then 32-bit microprocessors. So this would be a generic processor like the 8088 or the Motorola 68000 series processors. Like those microprocessors basically made the personal computer revolution happen, right? In the 1960s, those 16-bit mainframes, those 16-bit processors were all custom jobs, right, for that particular mainframe. But the availability of cheap, inexpensive microprocessors kind of revolutionized the industry. The very same microprocessor that, for example, Sun used in their Sun workstations, the Motorola 68000, was the processor that Apple used in their Macintoshes, their early Macintoshes. And it was also the same processor that a bunch of printer companies at the time, for example, Imagen, whom I worked for back in the 1990s, used for their early printers in the 1980s. So, it became this standard platform that everybody based their architectures on. You'll notice that 8, 16, and 32-bit microprocessors all happened very quickly, right? The 8-bit processors really started appearing in 1972, 16-bit just a few years later in 76, and by the end of the 70s, we had 32-bit microprocessors like the Motorola 68000. What's interesting to note is that 64-bit microprocessors didn't happen until over 15 years later in the mid-1990s. And what's interesting is that those 64-bit microprocessors didn't first appear in like PCs and general purpose computing platforms. They actually used in video game consoles first. And then, gradually generic 64-bit processors became available for the computers that we all know and love today. So it was really interesting. Like, we didn't need more than 32-bit processors for a really long time for general purpose computing. Although the video game people wanted to push the envelope more. And we were perfectly happy with 32-bit processors for the entire 1980s and much of the 1990s. So just interesting. Moore's law and all that stuff. Now, look, in the 1980s, when I was doing my undergraduate computer science, we talked about word size. Okay, so like if you were using a 32-bit processor, which is what we were using at the time in 1985, my first workstation was a Sun 3, and we used a Motorola 68020 processor. It was a 32-bit architecture. So the word size for that CPU was 32 bits, right? If you were using an older 16-bit processor, your word size was 16 bits and so on. That's the computer science definition of the word size. It is the data width of your CPU, whatever it is. But harsh life intervenes, and the reality is that 16-bit computers were around for a really long time, right? 16-bit mainframes were around throughout the 1960s and much of the 1970s. And so the term word became synonymous with 16-bit values. And if you are an assembly language programmer or reverse engineer, or you're a exploit developer, right? We talk at the assembly language level about bytes, right, which are 8 bits, words, which are 16-bit values. But then what if you're on a 32-bit processor? Well, we talk about D words, double words, so that's 32 bits. And now that we have 64-bit processors, we talk about Q words, quad words, or 64-bit values. And yes, 128 bits are octawords. Now, we don't have 128-bit processors in general circulation now, but that's what it's going to be. It's going to be octawords. My computer science professor is spinning in his grave right now, but that's just the reality. And so you'll hear people using these terms, right? D words, words, Q words, and that kind of thing, as you approach any discipline that uses assembly language. So there you go. Okay. The other thing that we talk about is byte ordering. You may have heard the terms big endian and little endian. Wondered what that's all about. Okay, so here we go. This one will drive you crazy because it drives me crazy. All right, look, we're human beings, right? And when we write numbers from left to right, right? So 2,047,986,293, right? The 2 billion is over here on the left-hand side, right? And the 3, right? The units, it's over here on the right-hand side, okay? That is the big end, right? The 2 billion is the big end, and the 3 is the little end. That's the way humans write numbers. Big end to little end. Same thing in hex, right? If I wanted to represent that number in hexadecimal, I'd pop it into my calculator, and at the end of the day, you get a hex number that looks like this. 7A11CA75. Okay, that is if you plug it in the calculator, that's the hex for this number. Okay, but we're still writing it big end to little end, right? That's the big end. There's the little end. Okay. We as humans generally use what we call big endian notation, right? Big end to little end. Intel processors use what's called little endian. The byte order is reversed. You write the smallest byte first, and then the next smallest byte, and so on. So in big endian, 7A11CA75. To write that in little endian, you literally write the bytes in reverse order. So in little endian, the first byte is the 7.5. Okay? Right? So the 7.5 goes first, and then the CA, and then the 1.1, and then the 7A, right? You're reversing them in terms of bytes, right? You're not just writing the digits in reverse order. You're taking them byte by byte and writing them the bytes in reverse order. It may help you to think about it this way. If the bytes are numbered 1, 2, 3, 4 in big endian notation, in little endian notation, the byte order is 4, 3, 2, 1. Yikes. Bonus points if you know the literary reference for big endian and little endian. I'll let that marinate in the chat for a while, and we can talk about it when we get to the exercise. But the big endian, little endian is actually a little joke that comes from a literary reference. So I went to a liberal arts school. I had to learn stuff like this. Anyway, okay, so that's little endian notation, right? And Intel family processors, since forever, have used little endian byte order. Why? Like, what the heck, right? Like why is this a good idea, right? Okay, it actually makes sense if you think about the way computers store and deal with numbers. So when you're programming, you sometimes want, just a byte. Sometimes you want a 32-bit value. Sometimes you want a 64-bit value. The computer doesn't really know or care in some sense. It just knows that your data starts at a particular spot in memory, a particular address, okay? So imagine the memory of the computer being just kind of like this infinitely long piece of paper. And it's divided into sections, which are the bytes, right? And in each section, each byte, you can store an 8-bit value, okay? So here is our number stored in little endian byte order, right? So first we have the 7.5, and then the CA, and the 1.1, and the 7A, okay? All right, so larger memory addresses to the right. Your data is referenced by the starting address, the first byte of your quantity, whatever that is. Okay, so let's say here's our start address, right where the 7.5 byte is. Okay, that's our starting address. Okay, with little endian ordering, if I want a byte, boom, there it is. I'm right on it. My starting address is the lowest byte, okay? But if I want a 16-bit value, let's say it's a port number, right? Well, boom, there you are. Just grab 2 bytes, the next 2 bytes in a row, right? Or if I want the full 32-bit value, boom, there it is, 4 bytes in a row, right? The little endian byte order allows the computer to help you select the data size you want without having to sort of reposition, right? If the bytes were the other way, if it was in big endian order, right, your start address would be the top byte, the high byte, the big byte, right? To get to the lower 16 bits, you'd have to kind of move ahead slightly in memory to get the lower 16 bits or the lower byte or whatever it is, right? But with little endian ordering, no matter where you start, you can grab as much data or as little data as you want without having to jump around in memory. And that is very convenient from a hardware architecture perspective, although it makes it harder for us as a human when we're looking at data in little endian byte order because we have to swap the bytes around. And this is, this drives me insane when I'm doing low-level forensics. Because I'm looking at something like the master boot record, or I'm looking at the master file table in an NTFS file system. And the values are there in my hex editor, but I need to reverse the bytes every time. Now, frankly, if you're using a good hex editor, the hex editor will do the byte reordering for you. You can just, select a bunch of bytes and say, I want to see the little endian decoding of this, and it'll figure it out for you. But if you're just doing it raw, it's just a hassle for humans to have to reorder the bytes. But this is why fundamentally the Intel family processors use little endian byte ordering, because it's more convenient when you're actually, processing the data on your processor, because everything's sort of in the natural order for the computer. Also, the other thing is, since you're starting on the low byte, it's easier to determine whether the value is odd or even, right? Again, if we were in big endian byte ordering and we were starting on the big byte, we'd have to jump to the last byte to figure out whether it's odd or even. But, in little endian byte order, boom, you're right in the place you need to be to figure out whether the number is odd or even, because only the last digit matters. So that is why little endian byte order, right? And believe me, I asked this question as well the first time I heard about the difference between little endian and big endian ordering. I'm like, holy cow, who the hell thought this was a good idea? But it makes sense once somebody kind of understands the layout in your computer. Okay. So how do you know? How do you know whether it's big endian or little endian? Because again, in some sense, like just looking at a bunch of bytes, you have no idea. The answer is it depends on context, right? So here is the context for different choices. Okay, Intel family processors use little endian, and frankly, that's the most common thing out there today. Intel has basically taken over processor space, but you may still have old legacy SPARC systems or MIPS or all of the HP RISC chips, right? All of those older proprietary chips are pretty much all big endian. The old RISC chips and things like that. So yeah, if you have some of those in your life, they're big endian, but most of the time you're going to be working on Intel processors. As a result, most of the file system data you're going to encounter on Intel-based architectures also uses little endian data. The one exception is XFS. XFS was a file system that was created by SGI back in the day for their RISC processors, their MIPS CPUs, and those were big endian processors. The XFS file system was written as a big endian only file system. So even on Intel, all of the data in XFS file systems is big endian, which is great for me when I'm using my hex editor. For you, you'll never know the difference because there are macros to convert the byte ordering. If you're looking at a PCAP file in a hex editor, assuming you captured that PCAP file on an Intel-based architecture, that PCAP file is going to be written in little endian byte order. But guess what? Packets on the wire are always in big endian, what we call network byte order, right? So if you're just looking at the raw data off the wire and not stored in a PCAP file, all that data is going to be in big endian. The data is converted to little endian when it's stored in a PCAP file on an Intel-based machine. Now, I mean, if you happen to have an old Spark box lying around and you create a PCAP file, it's actually written in big endian byte order. The PCAP format allows either one. And the way you tell is because the header, PCAP header, the very first field in the PCAP header is always A1, B2, C3, D4, right? And whether those bytes are in little endian or big endian order gives you a clue about what platform that PCAP file was written on. Okay. So PCAP files that you see most of the time are going to be in little endian byte order, right? So the first 4 bytes are going to be D4, C3, B2, A1. Okay. But every once in a while, you run into a PCAP file that was written on a big endian machine, A1, B2, C3, D4. Anyway, packets on the wire, always in network byte order, which is big endian. PCAP files created on Intel, little endian byte order. File systems on Intel hosts, all little endian except for XFS. And your processor is probably an Intel family processor. So little endian byte order. Great. Yeah, so there's some commentary from the Discord. That's why it's good to know the host system when crafting a buffer overflow, right? Oh yes, right. Byte order absolutely matters when you're crafting an exploit. Happily, most exploits are going to be going against little endian processor architectures, but yeah. Also, there's a question about will the next architecture be 128-bit processors? Or will we just bypass and go straight to LLMs and natural language processing? AI, what we're calling AI these days. Look, here's the thing. Those AI models, right, still have to run on some processor. And yes, I believe that we will probably get to 128-bit processors in my lifetime. It's just a natural consequence of Moore's law. So whether you're choosing to implement a large language model or other software, still needs a processor to run on, needs hardware. The stuff doesn't run on air. So I mean, yeah, I think we'll get there. Or we could go sideways and really create workable quantum computers, in which case things get hairy. But I think that we probably will see 128-bit processors before we have a fully working, production scale quantum computer. But my crystal ball is hazy, so who knows? Okay. So, practice exercises. So here's a fun one for you. These are actual extents in my hex editor from a ext4 file system, and I've tried to color them to group them. So each extent is 12 bytes. Remember, 2 hex digits is a byte, right? So each extent is 12 bytes. The first 4 bytes are the logical offset. So is this chunk 1 of the file, chunk 2 of the file, chunk 3 of the file, and so on. The next 2 bytes are the total number of blocks in the extent or cluster run, if you're a Windows person. Okay. And then the last 6 bytes are the address of the first block of the extent, right? So the way we specify the contents of a file, you have extents that run from a certain starting block and go for a certain number of blocks. And if you need to chunk that up in pieces, you can have multiple extents. And the logical offset tells you where each piece fits when you're putting the file back together. Okay. So ext4 uses 48-bit addresses. Why? I don't know. So you have the upper two bytes in the 2-byte field, and then you have the lower 4 bytes in another 4-byte field. Okay, so 12 bytes in total. What I want you to do is there are 6 extents here. I tried to color code them. I want you to convert each field from hex to decimal. Now, this is an ext4 file system on an Intel family processor. So all of these are in little endian byte ordering. So when you're converting, right? So this field, this 2-byte field, 0100, but it's little endian. So it's actually 0001, right? Okay, so I need you to do the byte ordering correctly and then convert it to decimal. And you can use a calculator for that if you want, because obviously you're not going to convert this 4-byte hex value by hand. So whip out your trusty calculator. But see if you can do that for all 6 extents. So there's 4 fields per extent, 6 extents. So that's 24 hex values you've got to correctly byte order and then convert to decimal. And that's enough practice, believe me. So I'm going to turn you loose on that the next 20 minutes or so. You may need more time on this one, or you may just give up and say, to heck with it. But we'll start with 20 minutes and see how people feel. Again, we seem to be good to go. I'm not going to go through all of these. Obviously, you have the answers. But yeah, let's just do the last one, shall we? Okay. So 4-byte logical offset, right? So, but it's in little endian. Okay. So 800000, got to reverse the bytes. So really it's 00000080. So that's an 8 in the 16s place. 8 times 16 is 128. Okay, so this extent fits at byte offset 128, or excuse me, block offset 128 in the total file length, right? So you can add up the chunks, right? The first chunk is only 1 block big, as is the second, third, and fourth. Each is only a 1 block extent. Then we have 124 block extent. Okay, so the last extent is going to start 128 blocks in. Okay, number of blocks, right? So that's 7C00, but got to reverse it. So 007C, so 7/16, that would be 112, right? Yeah, 112. And then add 12 more, so that's 124. Okay, so 124 blocks long. All right, the starting block. All of these extents, the upper 16 bits are zeros. I mean, you can just skip those. And then the remainder, so 0002, 06, 00. Right? And you plug that into your trusty calculator. That block offset is 132608. Okay, so that's, plenty of little endian decoding for you. But this is my reality, right? When I'm doing low-level file system research, and I'm actually looking at file data structures in hex editor, trying to puzzle out what's going on, I'm also constantly having to do byte swapping because little endian byte ordering. So yes, I understand it's easier for computers in general, but it makes my life a big pain. Well, okay. Last section.